Ah, so you've stumbled your way around AP Calculus, and would you look at that? The test is on May 12th. Did you really believe you can stuff an entire year's worth of material in just 1 hour? Well, it wouldn't matter anymore. Let's get this show on the road. Let's see if we can go over all 5 of the main topics of AP Calculus so that you'll be ready to take that test after our hour here together. So why don't we begin over with part 1, which is limits and continuity. Now, the AP test can ask you anything, and I mean anything, over the entire year in which you've been taking this class. And so, the question is, are you confident, like really confident, in being able to answer any sort of question over this entire year that you've been part of this class? Well, why don't we look at something like this? Oh dear, what is this? Is f of x continuous at x is equal to 0? And what's going on over here? This function is split up into 2 different parts. How do we solve something like this? Do we graph it? No. If you're looking to prove if a function is continuous at a specific point, there are 3 steps. And I mean exactly 3 steps for us to do in order to make that happen. Let's quickly go over them so that we have it on record here. Our first step to proving continuity for a function is that we need to take the limit as our variable x will approach that number in which you are trying to prove from the right side of that function, and it must be equal to the limit as x approaches the left side for that same function. Now, what does that mean? We'll get to there in a second, but the whole purpose as to why we care about looking at the right side and the left side is that we can prove that the limit as x approaches that number from both sides of the equation, so both the right and the left side, will give us the same exact answer. All right, that's pretty good, but now we have to go on to the second step. Our second step is that for now, when we go and get the function and plug in the number itself that we are trying to prove, that must exist. Okay, obviously it can't be a function that is continuous if the point isn't on the graph in the first place. So with that, we have our third and final step to prove that this is going to be continuous at the number that we're looking at, because from step number 1, that if we took the limit as x approaches the number from both sides of that value, and if that for the function is exactly equal to the point itself when you plug in for the number that you're looking at, if both the limit and the point are exactly the same, good job, you've proven that it is continuous. Not so bad. But now what about this guy though? We still need to solve for this exact problem. As you can see here, we've got this whole mess of x squared plus x over x on the first part of this function, but it splits on downwards to a simple 1 if we are equal to 0. So let's go over those 3 steps. We need to look at the limits as we approach both sides of the equation for this function to see if that will match. Well, let's have a look here. We can go and write down that we are taking the limit as x approaches 0 from the right side of the function x squared plus x all over x, and we're going to ask to see if that's the same as we approach it from the left side for the same exact function right there. So again, how do we solve a left and right side of 0? Are there a left and right side of 0? Well, of course there is. You need to think of it as if we were on a number line and we had 0, we are approaching from the left side or we are approaching from the right side. That is the idea right there. So you might think, well, okay, well, if it's basically 0 and we just plug it right in there, we'll get 0 squared plus 0 over 0. Oh, would you look at that 0 over 0? Huh? What's 0 over 0? And that's where a lot of students will make mistakes. This is not a good line of work because you end up with a place that you cannot get yourself out of. 0 over 0 is not a definitive value. Good enough for us to then show as an answer here. So you might think, well, what do we do? Well, you have to think about it. We are approaching 0 for these limits, but that also means that we're not equal to 0, meaning we can go ahead and start canceling out factors of x on both sides of this fraction so that we can get to a simpler answer and then plug in our limit. So let's follow this line of work here instead, where if we took the limit as x approaches 0 from the right side, but instead we can take out one factor of x from both the numerator, leaving that as 1, and the denominator, then we end up with x plus 1 over 1, and that will match as well on the other side, right? So if we do it on the left side of the limit as well, we'll get x plus 1 over 1. Now this looks plenty good for us to install that limit of 0 on both the left and right side, functionally being 0 for what we're looking at. In this case, we get is equal to positive 1 on the left side and positive 1 on the right side, with 0 plus 1 over 1 giving us a simple, easy 1. Well, it looks like we've checked off our first step right there, because we've shown that x approaches 0 from both sides will give us exactly 1 on either side of that limit. So we can make that note that the limit as x approaches 0 from both sides for the function is going to be 1. Very nice. But what about if we go to the second part? We need to look at the actual point to see if it exists. The point? You mean if we just plugged in f of 0? Does that exist? Well, we have to go back to the original function. If we plug in 0 into the function, do we follow the top rule or the bottom rule? And in this case, we will follow the bottom rule, because if x is exactly equal to 0, not approaching, but is exactly equal to 0, we will get a simple 1 based off of the rule. And when you look at that, that seems, instead of being an unknown, f of 0 becomes a positive 1. Oh! Nice. That's pretty good, because when you look at that, the function point and the actual limit are both equal to each other. So with our last line of work, we can show that the limit as x approaches 0 for the function on both sides is exactly equal to the function point if we plugged in 0 directly. And so we can make our conclusion that the function f of x is continuous at x is equal to 0. And would you look at that, our work here is done. That's pretty good. Well, that actually took a bit of time, but what about something like this? Ooh. Ow! What is going on over here? There's nothing to cancel. That's a sine function on top and an x on the bottom. And what if we actually go ahead and just plug in zeros? We'll get sine of 0 over 0, which again is 0 over 0. That is no good. What can be done here? Again, you have to remember the specific rules. We have a very special rule about dealing with sine over x when we deal with certain limits. And of course, this is the most basic rule for limits for AP Calculus students. We have, let's take a look here if we can remember. Our rule clearly states that if we have a limit and we use the variable theta to show that we're dealing with an angle inside of the sine function. So if theta approaches 0, of our sine of theta over theta, we get 1. That is the rule. There's other ways to look at this, but for the simplest case, that is simply a rule which we can use to reach our endpoints for our limits here. But wait a minute, this doesn't match up 100% with that. What do you mean? Because sine of theta and the theta in the denominator must be exactly the same in order for this rule to work. So what was the big deal? What are we doing over here? You need to start thinking like a math student. This is no way to just simply plug it right in there and call it a day. Obviously, we have 3x inside of the sine, but we only have an x there in the denominator. How can we solve for that? Well, if we took this line of work here and we realize that, okay, we are dealing with a fraction and we need the denominator to match exactly with what was inside of the sign. Well, this is simple algebra work, and it shouldn't take too much brain power for our students to realize that if we're dealing with sine of 3x on the numerator and an x in the denominator, you can simply, if you're looking to make coefficients match, multiply the entirety of this fraction by 3 over 3. Oh yes, because 3 over 3 is just a simple 1, multiplying any sort of value by 1 makes no difference. So with that, we get the limit as x approaches 0 for 3 times the sine of 3x. That is going to be the numerator, while the denominator does match what we were looking for as 3x. Okay, we're getting somewhere. But now what about this 3 right here as a coefficient of the sine? What was that? A coefficient? Well, would you look at that? We can split this guy right down here, and that's exactly what we want, but you realize that we're multiplying by a 3. Wasn't there a coefficient rule or something like that with limits? Of course there is, because we can split this up as understanding that we are taking the limit as x approaches 0 of a simple 3, but then multiplying all of this by the limit as x approaches 0. Now for the remainder of this limit of the sine of 3x all over 3x. Now this is the real business that's going on in calculus, because right here is exactly what we were looking for this to turn into 1. Of course, there is no x to begin with in the limit of 3, so we leave it as a simple 3 multiplied by 1, and we can finish this up with a whole 3. I say that's pretty good. Now we can conclude part 1 with one last topic here, and we shall see what that looks like right over there. Whoa, 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 what is happening here? We have a limit approaching infinity, and we've got natural log of x over 4x. What is happening here? There are no rules for something like this specifically. Well, indeed. A lot of times our students will take one look at this and go, all right, infinity, whatever. Let's just go and throw an infinity right into the sky. And so we get infinity over infinity. What in the world is that? And this is where we end up with the real problem here. Although the natural log of infinity does go to infinity, and of course 4 times infinity is also infinity, this also is not a good form for us to write down as an answer. With infinity over infinity and likewise 0 over 0, and neither of these are acceptable answers because those are what we call indeterminate forms. Meaning that we cannot, so indeterminate, again, we cannot determine what those ratios will turn into. Now you must appeal to a higher power, our good old friend L'Hopital's rule. This rule will be the main cause for concern if students don't know this one. This is the real deal dealing with trying to take away actual values from these limits. With L'Hopital's rule, we can go and realize that instead, if we have that limit as x approaches some sort of value of the ratio, let's call it f of x over g of x, right? So two different functions we can describe on the numerator and the denominator. Again, we are taking a limit. We just want to see if this approaches a value in which we can ascribe something to it. So because we have that, L'Hopital's rule means that we can denote that we are going to follow this idea that if we're looking just to see how to solve a limit, you can go ahead and take that limit and instead look at the way that the derivatives of the numerator and the denominator will result in. This right here is the real savior to a lot of students when they're stuck on these types of limits. But remember, the note here is that this only works, right? So only if, right, the limit goes to an indeterminate form. This wouldn't work if your limit already goes to a number that is already easily found. This has to be if that limit goes to indeterminate forms like infinity over infinity or 0 over 0. Okay? So in our case, this question does indeed give us an indeterminate form if we threw in the infinity immediately. So let's follow this line of work here. With the idea of using L'Hopital's rule to get us out of this bind here, we can tell that our limit, even though x approaches infinity, for the natural log of x over 4x, we can use L'Hopital's rule to keep the same limit because we haven't plugged in for it yet, but instead we can take the derivative of the numerator and the derivative of the denominator.
But I don't know derivatives yet.
What do you mean you don't know derivatives yet? We'll go over that in part 2. Right now, let's just assume that you do know how to do this. So remembering the natural log rule, that it will give us a 1 over x on the numerator and then a 4 in the denominator. Remember, this is not quotient rule. L'Hopital's rule is just taking the derivative of just the numerator and just the denominator separately to see which one will end up with a number as a result. So this looks pretty good because actually if we then evaluate it for x approaches infinity, we get 1 over infinity in the numerator, and in the denominator we leave it as a 4. 1 over infinity, now that is actually determinable with any sort of number being divided by an increasingly larger number, again, such as infinity being that value that we assign to it. We can realize that we have 0 in the numerator and then 4 in the denominator. And there you go. Would you look at that? We do end up with a possible value that this limit approaches 0 because, again, looking at the way that the derivatives on the numerator and denominator go, we will then ascribe to seeing which one will actually turn out to be the larger one. In this case, the denominator is larger, ending us with a 0 as a result. Very good. So I think with that, we can go over to the second part. Part 2, differentiation. Oh wait, you lost attention already? We have 3 more parts to go. Well, it doesn't matter. We will keep on steaming right ahead. Now, for legal reasons, here is the true definition of what a derivative is. But who cares about that? We just need to remember all of our differentiation rules and we will be good to go to start solving some problems. So let's see if you can keep up and remember all of these if I really rattle them off rapid fire right here. Boom! Exponent rule, where you go and take the result of a function to its exponent, bring it down, and subtract 1 from the exponent spot. Pretty neat. Boom! Product rule, where if you have 2 functions multiplied together with its derivative, you will go split it to 2 parts right here of the first function u multiplied by the derivative of the other function dv, then adding it with now the other way around of the function v multiplied by the derivative of u. Boom! Quotient rule, where indeed will be one of the hardest rules to memorize as a student, but will be no problem if you really stick it inside your brain, that if you have the division between 2 functions f over g with its derivative, you will go in the exact order of low, so the denominator, multiplied by the derivative of a high, less high derivative of the low, all divided by squared below. A really weird and corny saying, but no problem. Whatever it takes for our students to memorize this exact scenario is what we need to be done, because they will ask problems like this for sure at least a few times on the exam. Boom! The exponential rule, which will be e, and of course the Euler's constant, e the 2.71 blah blah blah, doesn't matter. If you have e raised to the u with that derivative, you will then leave it exactly the way it is with e raised to the u, but then multiplied by the derivative of what was inside of that exponent spot. A little foreshadowing to chain rule, but first we need to get to, boom, the natural log rule, where if you have the natural log, so logarithm base of e of u, and you take that derivative, it will be 1 over the u times the derivative of what was inside of that natural log. Now one last one of a whole slew of these guys, the trig rules. We have 4 that are the most common, and there'll be some other ones later on, but the most basic ones will be that sine derivative goes to positive cosine, But the positive cosine, that derivative becomes negative sine, and then going over to the other side, we have the tangent derivative going to secant squared, and then secant derivative goes to secant times tangent. All of these are rules in which need to be memorized and practiced for our students to then increase their skill on this exam. But wait, before we finish this off, looks like we have the whole beast of the problem, right? Chain rule. Oh man, that's right. This is the last business to deal with. If you have a function in a function and you take that derivative, then you go through the exact steps of f prime of g of x, leaving that inside there, but as a coefficient multiplying by the derivative of the function that was inside to begin with. That's right. Looks like we are just about good enough to go into some real problems, which we can get this. Oh man, we have right here this problem in which a lot of students might forget on the day of the exam. We have the derivative of an inverse. Now let's go over the rule first and then this example here on the bottom. So it states here that if we have the inverse of f, being that if you plug in b of the inverse of f, you get f of a. So remember, if we plug in basically the y values into the inverse, we then get the resulting x values of that function. So we can then draw up the conclusion here that if you took the derivative of that inverse function of f, it will then be the same thing as if we did the inverse of b with that derivative. We take the 1 over, so again inverting with throwing it to the denominator of f prime of a, though again that's the resulting from inverting the results of b back into a. Confusing, I know, lots of things going on with inverses and back and forth and blah blah blah. So let's get right into an example problem to see how this all turns out. First, it tells us that g is going to be the inverse function of f of x, but they define f of x as x to the third plus x minus 2. So in that case, they want us to evaluate g prime of 0. So one thing to note, of course, is that if they're looking for g prime of 0, the best way to go about this is that we need to make a table of values right here. So something to note is that if we have g, again inverting of f, right, we need these separate values. So if we plug in an x into these guys and then we get an f as a result, then we need to know what the result is if we did it from g backwards into f. For example, if we wanted to start with 0 on the x, right, if we plugged in 0 to f of x, we get what, 0 plus 0 minus 2. So that will be a negative 2 on the f. But in the sense of plugging 0 into g, right, so if you plug in 0 to g, we need to know, right, what the f result is if instead the f result was 0 and what that x must mean, right? So the idea is that 0 on the g must also be, right, the resulting 0 in the f, so that we can see what the resulting x will be on that sense. So for example, if we set f of x to be equal to 0 and we solve for x to the third plus x minus 2, just a little bit of number finagling and all that business really just means that we need ones across the board, minus 2. So in this case, if x was equal to 1, f will be equal to 0. So in that case, we can make the relationship that g of 0 is equal to 1. Remember, is that you plug in the y values into the inverse and you will get the resulting x value as a result. So with that all sorted out, we need to then see what the derivative of g is going to be. Thanks to our rule that we've written out right here, g prime of 0, so the derivative of the inverse, is the same thing as saying we're going 1 over the derivative of f, but not at 0 though. Again, we need to go reverse, so we need to plug in the y value instead into f because we are inverting what is being plugged in. So that's the f prime of 1 that needs to be solved for right there. Well, we only have the original function of f. So it looks like we need to take one other step here to take the first derivative of f in order for us to then solve for this guy. So that's going to be 3x squared, dealing with the x to the third power with exponent rule, plus a 1 with the x, and of course the negative 2 goes to 0. Derivative of any singular constant number will give you 0. So with 3x squared plus 1 being there, we just need to plug in for a positive 1 into this scenario, giving us 3 times 1 squared plus 1, giving us a positive 4 as a result. So we do a simple substitution here, and so g prime of 0 is going to be 1 over a positive 4. And there you have it. The derivative of an inverse function. Could very well be asked in the exam. They don't ask for it all the time, but because there are just so many multiple choice problems on the exam, you never know, and it's best if you did know this in the back of your head. So lastly, let's get to the real big hitter of the purpose why we do this differentiation subject with this guy. Oh man, mean value theorem? We have to memorize a whole theorem? Yes, yes indeed you have to, because we are dealing with the specific rulings and mathematical guarantee that certain points exist. So once more, for legal reasons, we'll have to read the whole theorem, but let's see what that looks like if we were to take a simple gander at some problems. If f of x is continuous on the closed interval a to b and is differentiable, f prime of x, of course that's what that means, on the open interval a to b, then there is at least one c on the interval between a to c to b, such that f of b minus f of a over b minus a is equal to f prime of c. What did all of that mathematical nonsense mean in the first place? Well, once more, let's take a look at the important bits right here. Right? We must show that it is continuous and differentiable. Those are the requirements for this theorem to be true. Then, because of that, across the interval that we're looking at it, that we can guarantee at least one C. That is capital G, guarantee that there is going to be a point C in between A to B where we have this equation holding true. What is this? F of B minus F of A over B minus A. Some people might call it, oh, it's a slope between 2 points. That's one way to look at it. The other way is that we can give this a name as the average rate of change, right? Again, some people might even call that slope nonetheless, but it is the rate at which we are changing because it's the change in y values over the change in the x values, if you want to look at it that way. But the next part is that it is then equal to a derivative. That's right. There is actually a relationship to be had between the way that a linear slope is going between two points, that is, and the actual derivative on a single point. As again, with the derivative function, you plug in a single value, you will get one back. What does that even look like? Well, let's have a look here. What if we drew some sort of imaginary function here, which in between, if we go from point A to point B up there, okay, and this function very well could just go something like this. So it's not exactly a line, it's not linear, but it is a continuous and differentiable function. Well, if we were to go and take a look and you realize, okay, well, the derivatives could be anywhere. Again, those tangent lines go left and right and all over the place. But what about instead we took a look at the actual average rate of change? So if we just drew just a singular straight line between A to B, we have that average rate of change. Obviously, with a singular line, that's going to be the case. Well, thanks to mean value theorem, again, given that this function, if we call it f of x right here, because it is a continuous and differentiable function, it is guaranteed, capital G, guaranteed that there is going to be at least some form somewhere on the graph which we will call point C, that if we took the tangent line, right, the slope specifically on that singular point, it's going to be exactly, and I mean exactly equal to the actual average rate of change. You may call it M for slope, right? But the actual slope between those 2 points being exactly equal to that first derivative. Sounds kind of weird, sounds kind of useless, but we shall see how that looks like on some actual free response questions, which now, as a shameless plug, you can see right here on my YouTube channel, labcodemath@gmail.com. We are live from 4 to 7 p.m. Pacific time on Tuesdays and Thursdays, going over problems which are going to ask exactly this on the free response side of the AP Calculus test. What? You thought we were done with derivatives? Absolutely not. Our third part is fully dedicated to the applications of derivatives, in which we need to be able to respond to the free response questions on the exam. You can do a derivative? So what? Can you still answer the real questions like something right here? Critical point? What's that? Well, looks like we need to go conjure up some definitions right here. And there we have the 2 rules for a critical point. Let's go over them. First off, we are going to look at any point n, but in this case, it must be so that the first derivative f prime with n plugged into it must be equal to 0. That's pretty simple, but secondly though, this also must be true for a critical point to exist, is that at that point f prime of n, it must cross the x-axis specifically from a positive to negative sign or a negative to positive sign. What does that look like for us? Well, if we were to think of some arbitrary graph here, where we were graphing f prime of x, is that critical points would only exist if we have the graph, in this case here, crossing from a positive side to a negative side, or in the other sense as well, from the negative to the positive side. Those 2 would be critical points that we can point to then mathematically prove. Of course, the issue though is that if you have some part of the graph which goes up and touches and returns back from negative to negative again, that is no good. That is not a critical point. We must have it go to the x-axis, touch it, and then cross over to the other side, switching its signs. So with that, we should have enough to actually go about solving this problem here. So of course, obviously, as we see through these rules, that we need to find the first derivative of that function f. So let's go ahead and do that, right? Following this line of work from the problem, that f prime of x, then if we use all our lovely exponent rules that we can follow, we get 6x to the second power for the first term, then subtracted by 6x on the second term, and then subtracted by 12 on the third term. Pretty easy to follow along. Then of course we can go ahead and start factoring this out, so we can start looking for zeros in an easier sense right here. So it's 6 multiplied by all of x squared minus x minus 2, and then closing this out, we can factor using some simple algebra factoring that it's going to be x minus 2 as the first factor and x plus 1 as the second one. Again, with critical points, we are looking to see to make sure that the first derivative is equal to 0, so that those x values then can be obtained for possible critical points. So with step number 1, we can complete that. If we know, of course, with everything being a multiplication, any one of those terms need to be equal to 0. So in this case, x is equal to positive 2 or negative 1 will be possible critical points. But again, keyword is possible, because why? We need to see that it will cross the x-axis from changing its sign on the first derivative for these to be confirmed as critical points. So something that we like to do over here, especially to show all of our work, is something known as a number line analysis. This allows us to look at it visually, as well as seeing what the steps will look like if we took those zeros and placed them on a number line. So starting from least to greatest is -1 and +2. Again, this is x that we're dealing with for the values. But of course, because we need to know the signs of the first derivative, that's what we're going to plug into. The idea is that because these are zeros, so obviously 0 at -1 and 0 at +2, we're going to test some numbers in between them to look at the actual signs, again, if it's positive or negative, to see if it changes going across that 0 to prove that it is a critical point. Let's first begin here that we need to look at a number less than -1. So possible will be like -2 that we can throw in here. So keeping our eyes on that first derivative, that's all factored out quite nicely because that can keep us online with those signs right there. With the -2 plugged into this first derivative there, that gives us basically a 6 multiplied by a negative number, right? Because it's -2 minus 2, and the -2 plus 1 is going to be another negative number. And so with that, we get 6 times a negative times another negative. We only care about signs, the value not so much right now. So that's a positive value with all the numbers less than -1 for the first derivative. Then for a number in between -1 and +2, we can plug in the number 0 to have a look at the sign in between those two values. So once more, this is going to be 6 multiplied by a negative number because it's 0 minus 2, but then multiplied by a positive number afterwards with 0 plus 1 inside the first derivative. Positive, negative, positive, giving us a negative number. And lastly, with the number greater than 2, we can choose something like 4 if we want to. And we're going to see what the last result is going to be. So with a 6 as a constant coefficient, we have the 4 minus 2, making it a positive number, and then a 4 plus 1, making it another positive number. So now, with any number value greater than 2, we are multiplying with positive, positive, and positive, making it a positive sign for the first derivative. And would you look at that? We have exactly what we need to prove that -1 is a critical point and +2 is a critical point because, again, those are the 0 numbers, right? So that's the first rule for having 0 on the first derivative, but also they will be crossing over and changing signs, proving it the second time. Now, of course, what we need to realize is that what kind of critical point is it, right? This question doesn't exactly ask for it, but nonetheless, that's something that these questions will ask for on the AP exam. So if you look at the increasing then decreasing, because we're dealing with the first derivative, right? Going from positive to negative, right? That means that -1 here, because we're shifting from a positive first derivative down to a -1, we are dealing with a maximum here. And then on the other side, with the +2, with a negative going into a positive, right? So think of it as a decrease on the function going to an increase on the graph. That makes +2 a minimum on that side. Okay, so with that, we have proven that we have found the exact x values for those critical points, and that should be good for that part. Now, moving forth though, we need to look at this problem. What is happening here? The equation tangent to a curve? Oh, that is too much. Or is it? Once more, we must refer back to some definitions for us to help out on this type of problem. Tangent line equation, of course, meaning that it's going to be a straight line touching this curve at exactly one single point. Well, how do we get an equation of a tangent line? Very simply, it's going to be a straight linear line, most often best shown as point slope form because that's what the AP test graders usually like to refer to. So the way that we set it up is going to be something like this. This is how you get the tangent line equation with y is equal to m multiplied by all of x minus h plus k, of course, where m is going to be equal to that actual slope at a specific point, using the first derivative, of course, because we're finding the slope at a very specific point at h, where, of course, the point given is that we have h comma k given as the point of tangency for this problem. Okay, so with that, all it really is just a few bits of plugging in, finding the first derivative, and showing our answer without any sort of problem. So of course, as always, we need to look at the first derivative because we need to know the slope of that tangent line at the given point. So let's go first and do f prime of x, which turns out to be 3x squared minus 6 times x. But again, one time each for the exponent rule for the first derivative. Then, of course, we need to then plug in for the x value to find that slope at a specific point. So now we will plug in for f prime of 2 because that is the x value at the point that they're looking at. So f prime of 1 becomes 3 times 1 squared minus 6 times 1. Pretty simple. This becomes a 3 minus 6 and a negative 3 as a result. Again, that is going to be the slope. Now that he gave us the point at 1 comma negative 2, so it looks like we have both m, h, and k thanks to that point, and we can plug everything in and call it a day here. So with y being equal to the actual slope of negative 3 all multiplied by x. Now remember minus h, it's in the minus form, so it's minus 1, and then plus k, leaving it as is. So in this case, it will be just minus 2 at the end of it. And would you look at that, that is going to be the tangent line equation for this curve at that specific point. Usually the AP test will kind of egg you on a little bit further, asking you to approximate for a specific number after the fact, which is going to be a very simple plug in. Of course, you can tune into the live stream on Tuesdays and Thursdays to see full-length problems, including things like this, to be worked on in real time. Nonetheless though, what if we actually increase the heat a little bit on this guy and do a type of problem like this? Whew, this guy's crazy. Oh no, what are we gonna do? I'll tell you what we're going to do. It's time to relearn how to do something known as implicit differentiation. Yes, indeed. This is going to be another method of doing a derivative, especially when we have x's and y's all mixed up together in a huge mess, and we still need to find that tangent line equation nonetheless. So let's have a look here. How then can we take a derivative with things with x's and y's all in there together? Well, you might have seen this before in other problems, but we can use the form dy over dx. So again, the change in y in respect to x, that is going to be a result of the first derivative, but only for the y taking its derivative, while on the other hand, if we had x taking its derivative, it will simply go to 1 like how we've always done. That is the best way of memorizing the rule here because we are looking for the change in y over change in x. And so with that, we can isolate for this being the result of the first derivative and then leaving everything else in its own form after taking that first derivative, making life quite easy. Nonetheless though, we've got a lot of things to do, which of course, not only do these rules count, we must always remember that chain rule is going to be the paramount rule that we must follow for us to not make any mistakes. So let's get right to it. Obviously, we still need the slope of that tangent line, and then we need the point, which we'll get to in a little bit. So if we took the entirety of this equation and took the first derivative of it, let's see what that looks like. Oh dear, just to begin with, it's x squared multiplied by y. That's going to need some product rule because those are two variables which are being multiplied together. On the other hand, we have the y cubed on the right side, which means we still have to use exponent rule as well, but still keeping track of chain rule when needed. Let's get started here. So with x squared multiplied by y, we do product rule, where we do x squared. Now, this guy needs to have its derivative taken, so instead of calling it x squared, it's going to be 2 times x. We leave the y alone. Then we add that with the derivative of y, which remember, it no longer goes to 1. It's going to be dy over dx, leaving x squared completely by itself. Then the derivative of minus x becomes minus 1, very simple. And then the y cubed waiting for us on the other side of the equal sign then becomes, instead of just not only is it 3 times y squared using the exponent rule, but also chain rule because we need to then take the derivative of y itself, leaving us with a coefficient of dy over dx, and then subtract by 0 because the constant number 8 with its derivative just simply goes to 0. This right here is indeed a little bit of a mess, but all we need to do, remember, is that we are looking to isolate all forms of dy over dx to one side of the equation. So what we can do is that because that's already left on its side, we can just simply move over the x squared dy over dx to the right side, and everything should be followed with some bit of isolation after the fact. So with 2x times y minus 1 being equal to all of 3 times y squared of dy over dx, now subtracted by x squared times dy over dx, we can then have dy over dx isolated and move the rest by the denominator, leaving us with 2 times x times y minus 1 over the 3y squared minus x squared, leaving dy over dx factored out and leaving there by itself. Okay, so it looks like the first derivative is a little bit of a longer equation, but it's still something we can work with anyways. Oh, but what have we almost forgotten? That they did not even give us the y coordinate for this point. They only gave us the x value instead. Well, looks like we need to go take one more step ahead and plug in for x being equal to 0 so that we can find that y value. And because we need to plug in both the x's and the y's into the first derivative, then to find the slope. So over here, we're just going to need to do a little bit of side work here, plugging in the 0. So we get 0 squared times y, subtracted by 0 on the left side, and then y cubed minus 8 waiting there on the right side. Thankfully, all this goes straight to 0 on the left side, leaving us with y cubed minus 8 being equal to 0, which simple enough is just y being equal to a whole 2 as a result of us solving for that and still remembering that x was equal to 0 to begin with. So that is the point in which we will be finding the tangent line equation. So both of those values then need to be plugged into the first derivative. So in our case, our m is going to be, right, the slope at that specific point. We plug everything in, so it's going to be 2 times 0 on the x. Y is positive 2, subtracted by 1. That's all the numerator. And then the denominator becomes 3 times y being positive 2, all that squared. And then x being subtracted by 0, and all of that squared. Okay. So we end up with 2 times 0 times 2. This first guy goes to simply 0. We have a negative 1 in the numerator. This, of course, goes to the subtraction of 0. So 3 times 2 squared is a positive 12. So in this case, the slope for this line is going to be negative 1 over 12 as a result. Okay, so we have the x and y coordinate. We have the slope finally at the specific point. So it looks like we just need to throw everything together for us to then find that tangent line equation. So we of course follow that same exact form of point slope form. So y is equal to that slope of negative 1 over 12. Then x minus h will be minus 0, with the x point being 0 for h, and then plus 2 as the k. And there you go. That is going to be the tangent line equation to a differential equation, in the sense that we had to implicitly differentiate the dy over dx as a result of the derivative of y, because we have a full equation with x's and y's together in that curve. That doesn't sound too bad, but still something that needs to be practiced by our students for them to be able to answer this on the exam without a problem. Now, looks like we're picking up speed. Speed? Speed? Oh, what is that? Position, velocity, acceleration? Are we doing physics? Partly, but also it's still something very valid for the AP Calculus exam to start asking for. So we have this relationship here. If we started with the function of x known as position, take a derivative in respect to time, we then get velocity. One more derivative gives us 2 acceleration. That's right, you'll be taking 2 derivatives to go from position all the way to acceleration, and that relationship will be asked about on the test for sure. But where's speed though? Well, isn't speed more just like the exact same thing as velocity? Absolutely not. That right there is a case of math brain taking over the physics brain. We've got to follow this little bit of rules over here for us to then fully understand if they ask for speed, it will be not the same as velocity. So let's get to this rule first. If they want to know if a particle moving along a line, if it is speeding up or slowing down, speed is going to be the relationship of both the velocity and acceleration in something like this. Here we go. The 2 scenarios of speed up and slow down. A little bit off to the side here, we can see that we are speeding up if both the velocity and acceleration at the specific time that you're looking at the particle. If they are both positive or both negative, they are speeding up. It does not matter about the values, it simply matters about the sign for, again, both the velocity and acceleration. Of course, inversely, if velocity is positive at the time and the acceleration is negative, so different signs, in either case with velocity being positive, acceleration being negative, then on the other side with velocity being negative and acceleration being positive, that is enough to conclude that it is slowing down. Again, that relationship between both velocity and acceleration are both very important because speed does not care about the direction, while velocity and acceleration do. So if that were the case, if we just simply looked at something like this, is a very classic example for a position which was given as x of t being equal to 2t to the third power minus 9t squared plus 12t minus 4, but they want to know if it is speeding up or slowing down at time is equal to 3. Just like we've stated, we need to go look at both the acceleration and the velocity together for us to make that conclusion. So with the velocity being the first derivative of position, we just go ahead and start doing derivatives all across this equation, giving us over here 6t to the second power for the first term, minus 18t for the second term, and then plus 12 for the third term. Pretty okay, but not only that, we need to take this guy's derivative as the second time we do it for us to then get the acceleration as well, because we need to compare both. So going again, this is going to be 12t to the first power minus 18 as a result over there. Okay, so again, because we're looking at the exact time of 3 for this particle, we then need to go look at the velocity at the time of 3, plug everything in, as well as comparing it to the acceleration at 3 as well. Okay, so a simple plugging in will give us 6 times 3 squared for the first term, 18 times 3, and then plus 12. So the exponent goes first of 9 times 6, giving us 54, minus 18 times 3, which is another 54, and then plus 12, giving us a nice canceling right there, and a positive 12. That is a positive result for the velocity. Then comparing that alongside the acceleration, so plugging in 3 into 12, subtracting 18, so 36 minus 18 will give us positive 18 as a result over there, making that positive as well. And would you look at that, both velocity and acceleration are positive, leaving us with only the conclusion that the particle is speeding up at the time is equal to 3. Okay, and there you have it. That should do it for part 3 for the applications of derivatives, knowing that we can take multiple derivatives across the board here, and as well as making the connection towards the idea of particles along a straight line. So let's get on to part 4. Here we are with the real roadblock of calculus for many students, integration. Now, what we have written up here is that a test to see if students don't understand the difference between this guy and that guy. If there's any difference at all, you might as well go home if you can't see the difference here. Obviously, there are many rules to integration, but the two biggest ones, of course, is understanding what the answer to this will look like versus the answer to something like that. And so, without any further motion here, let's go to the rules right here. So let's have a look here. The first main idea that all students must understand is that if the derivative is known for going forward on an equation, in the other sense, integration is then going backwards. That relationship is extremely important, especially if you're looking to either check answers or answer certain problems. Then, going forward, an indefinite integral, the ones without limits, of course this guy over to the left, there's no limits of integration, will always end with a plus c as the answer of the constant of integration if you do it indefinitely. Okay, Then secondly though, is that a definite integral with the limits defined right there will then have the actual area underneath the curve from those limits and will usually end with a numerical value. Not always, but usually the result of integration is going to give you a full numerical answer as the area underneath the curve. Good. So now that we've set that, perhaps we can actually go and look at the differences of those two integrals to then see in real life what those differences will look like. So let's get first started with this guy over there on the left. If we're integrating e to the 2x subtracted by on the outside 2 times x squared. Integration is its own skill independent of differentiation, but they're still closely related, in which if you can keep up with the way that the answer derived will match what we have inside, we should be good to go. So with e raised to 2x, we obviously still remember the exponential rule, that it will stay exactly the same. It's just that thanks to chain rule, we must account for the 2 coming down as a coefficient. So to counter that, we just throw in a 1 over 2 as a coefficient there, because if you took the derivative of 1/2 e to the 2x, that'll match exactly as e to the 2x inside, making our check complete. Then with the minus 2 to the 2 times x to the second power, that's going to be 2 times x to the third power, making sure with exponent rule we're going to add 1 instead of subtract 1, and keep with a 3 in the denominator to match that 3 coming down as a coefficient if we were to take the derivative of that expression. Now, as always, the most common mistake is students saying, oh, we're done here, we don't need to do. Stop! We have to make sure that we have plus c written there as the result of the indefinite integration, because there are no limits to the actual integration and we don't know where this function actually lies on the graph. That plus c is the real deal breaker for a lot of students who simply want to go on to the next question. Now, with this being now a substantial answer to the first part, let's go over now to the definite integral over on this side to see what we need to do there. Of course, with limits now, we need to evaluate based on those limits. We can copy over the results of the indefinite integral because the integration is still exactly the same the way that it should be. So it's 2/3 x to the third power. We no longer need a plus c because we're taking the area underneath the curve entirely. So with that, we just need to show that we will be evaluating the limits from 0 to +1. Good. So what this means now is that we will subtract this from the upper limit, from the bottom limit, and we plug in for both sides, so everything plugged in 1, then subtract it with everything plugged in for 0 to then find the area going across here. So with a +1, this is going to be e raised to the +2 power, subtracted by a 2/3 as the first part of this analysis. And then with plugging in 0, we're going to subtract this with 1/2 times e raised to the 0 power, and then subtract it by 0 after the fact. Okay, so that looks pretty okay for now. The zeros over there, e raised to 0 is going to give us a +1 as a result, subtracted by 0. So it's going to be now, as a result for this last bit here, 1/2 e to the second power, negative -2/3 minus another half there. In that sense, will then give us a result of minus, in this case, should be, with the 2/3 being 4, 6, and 3, 6, so it'll be -7/6. Okay, there you go. So this is going to be the result of this work here. And with that, that will get us started for the way that we get to look at integrals, especially if we move on to a topic such as this. Riemann sum? What is all that nonsense? Indeed, there will be times in which you will be asked to approximate areas, especially if you're given only a table of specific values. So we don't have the actual equation, but they still want us to approximate a specific area given the exact constraints that they are looking for. Approximation? Area? Sounds like a bunch of nonsense still, but nonetheless though, this is the right strategy to use, especially with the different techniques that they're asking for of a right Riemann sum, left Riemann sum, or a trapezoidal sum for this. Again, now we're going to take a step back into the world of geometry to understand that if we have some sort of function listed out here, we can go and make little rectangles here to then approximate the area underneath the curve between specific values. Not too bad, but then that just means our algebra work needs to be on tip-top shape for us to then get the areas of these rectangles. For example, of course, if we want to find the area of a rectangle, that is going to be very simply, obviously, the most simplest of areas of a base multiplied by a height. And of course, because we are using 3 subintervals, we need to do it 3 times, 3 rectangles all added up to then give a response here. Now, of course, if they're asking for a right Riemann sum for these 4 points, allowing us to make 3 rectangles, the right Riemann sum means that the heights across are going to be the right side points, so 1, 2, and 3, ending on the rightmost value. And then we need to multiply by the bases by pairing them up going down. What does that look like? Well, with the right Riemann sum, we can set up the equation of the different bases, then multiplied by the heights. As you can see, the distances of them are going to be a little bit different, so we need to make sure we keep track of that. So with the first base being the difference of 3 minus 1, because the distance only between 1 and 3 is going to be a base of 2, then multiplied by the right-hand height of 6, adding that next with the next base of 7 minus 3, the distance between those two, and then multiplying that with that height of 8, and lastly, the third rectangle of being 9 minus 7 on the base, multiplied by a positive 5 as the height. Again, using the right-hand heights there will then confirm for us that this is a right Riemann sum. Then by doing a little bit of algebra work of first understanding we're dealing with a 12, then a 4 times 8 is 32, and then another 2 times 5 is 10, we get the total amount of 54 as a result of that sum. Then on the opposing side, using a left Riemann sum means that we're going to use the left-hand heights instead as the heights, but still the same exact bases. So we can actually carry on from the previous work because the subintervals are exactly the same. The first base of 2 from the first equation, then instead swapping it over with the left-hand height of 5, then the next one with the base of 4, with the left-hand height of 6 this time instead of 8, again choosing the left-hand side of the heights, and then lastly finishing it with the base of 2 multiplied by a height of 8 right there. Okay, then with the work here, it's going to be 10 and 24 and 16, giving us exactly 50 as a result of that line of work. And then one last bit, of course, is that we have to do trapezoid. Trapezoid? How do you do that? Well, think of it like this. If our functions instead didn't have nice flat rectangles, what if we had a nice dashed, or in this case a diagonal trapezoid with a horizontal base still? We can find this area to match a curve a lot nicer for the most part. But then how do you find that area? As you can see, for a trapezoid we have 2 separate heights. We have height 1 on one side and height 2, and then we still have the same exact base coming across. So the trapezoid has a nice little form of how to put this all together, with the base multiplied by, instead of just one height, it's going to be the height 1 plus height 2 all divided by 2. It's going to be the average of the 2 heights being multiplied by the base, so then you can find the area of a trapezoid that way. Very simple for us because, once more, the bases are exactly all the same. It's just that instead of just calling a 5 or 6 based on whichever form it is, it's going to be the average of the 2. So it's 5 plus 6 all divided by 2. Then going on to the next one, the next base is 4. Then with the 2 heights being 6 plus 8 all over 2. And then lastly, we have the last base of 2, and then the 2 separate heights, 8 plus 15, not 8 plus 5 that is, all over 2 like that. Okay, so remember, it's the average of each pair of heights along with the bases being paired. But then we can work our way around simplifying this guy so that we can then end up with our lines of work here being a positive 11, and then with a 14 times 2, so that's going to be 28. And then lastly, the last trapezoid will give us a 13, giving us our final result here as 52, adding all those 3 numbers up. They're all pretty close to each other, but of course the idea is that we are finding ways to approximate areas underneath the curve if we did not have an actual equation to go off of to do a definite integral. Pretty straightforward, but now what if they asked you something very legal like this? Ooh, average value? That sounds like something you should know, but kinda not, but also of a function across an interval. Oof. But yes, the calculus test loves asking this guy because once more, it's a test of knowledge. Once more, for legal reasons, let's write it out. The average value has a very simple equation that we're dealing with, which is going to be a nice coefficient as the defining factor here of 1 over b minus a for the definite integral from a to b of a function. And that's really it. Oh, really? People forget this? Believe me, I've seen far and wide that many students have no idea what average value means of a simple function with a very simple equation that can very easily be memorized. Again, as a little reminder, they do not give you these equations on the exam. You need to figure that one out yourselves. And so, with something like this, it should be very easy for our students to then come up with. Of course, the limits being, in our case, from -4 to +4, it looks like all we need to do is set up a lovely definite integral for this function, and we'll be home free. So let's have a look here. If we wanted to take a crack at this problem here, we of course need that coefficient there of 1 over b minus a. So remember, we're going from higher to lower. So it's 4 minus the other limit of -4. Keeping track of those signs, very important. Then we are going from now, again, from low to high. So it's from -4 to +4 for the function of f of x, which is going to be the cubic root of 4 minus x dx. Now this takes just a few steps in terms of definite integration for us to get through. So let's see if we can put everything here together. That coefficient, of course, in the front of 4 minus -4 makes it 1 over 8 as a positive value. Then for the integral, actually for something like this, just to keep in mind that we're dealing with the cubic root of this integration. So if we were to take our crack at integrating something like this, this is now going to be the 4 minus x, all of this, instead of to the 1/3 power, keeping in fact of the idea that a cube root is just a 1/3 exponent, giving this a 4/3 exponent, and then making sure with a negative coming out, if we were to take a derivative thanks to chain rule, and the 4/3 coming down from the exponent rule, we will need a coefficient of 3 over 4 with a negative there to cancel that out. There is no need for plus c because we are defining the integral from -4 to +4. Okay, a few steps waiting for us, but first we can kick out that coefficient because that's going to be same on both sides. So let's continue our line of work here with a -3 over 32. Then going forth here, so our first limit is going to be the 4 minus 4 raised to the 4/3 power, and then subtracting it with the other limit now of 4 minus -4, all of this still raised to the 4/3 power. Okay, a little bit more cleanup with a 4 minus 4, this guy going straight to 0, but a 4 minus -4, meaning that we have, with that coefficient weighting there, it's going to be a negative all of +8 raised to the 4/3 power. Okay, with 8 now dealing with a 3 on the denominator of its exponent will then give us a 2 waiting for us on the 4th power, giving us, with the negatives now canceling out, again a lot of work that we can easily run through. That's going to be 3 over 32 multiplied by 16, giving us 3 over 2 as a result of our integration. And there you go, that is average value. Again, if we were to actually take a look at the graph, you would see that the actual highs and lows of the graph will give us something around 3 over 2 if we averaged out the total area going across that interval. Very nice. And so with that, I think one way to cap off this part with integration is to look at one exact problem from a previous exam coming right. Whew. This guy's nuts. What? Solving for the actual original function f of x with this differential equation of 1/2 times sine of pi over 2x all multiplied by the square root of y plus 7. Whew, this one's a real hot one, isn't it? But indeed, this exact problem was on an old AP exam. Fair game for them to ask you exactly something along the lines of solving for the original function with a differential equation. Oh dear, this one will require us to stay calm, stay collected, and figure out how to solve this guy. So, if we have the differential equation right there, as you can see, there's x's on this side and y's on the same side. But as you can see, this is dy over dx. This is where we need to do our step of something known as separation of variables, because all of the things with y needs to match up with dy, and all the things with x needs to match up with dx. And then, believe it or not, just like how we can do a derivative of both sides of an equation, we will do an integral of both sides of the same equation. So let's have a look here. If we have dy, now instead if we swapped over that y plus 7 in the square root into the denominator by division, this is going to be dy over the square root of y plus 7. Then by multiplying the dx to the other side, we can get it set up with 1/2 times the sine of pi over 2 times x, all that multiplied by dx. Okay, now it's starting to look a little bit better with everything again on the x's with dx, everything with the y's with dy. And would you look at that, we can run an integral on both sides of the equation. That's right, we need to do one after the other, making sure that it's indefinite. But in this case, we only need plus c on the side of x, because we will then be isolating for y in the term of f of x after the fact. But nonetheless though, we have this waiting for us. Remember that this is square root of y plus 7 in the denominator. In the other case though, this is basically the same thing as saying it's y plus 7 all raised to the negative 1/2 power. And so with that, we can keep that in mind when we run this integral, meaning that we end up with y plus 7, now just raised to the positive 1/2 power, and of course making sure we have that coefficient of 2 waiting for us after if we were to ever take the derivative of that result. Then on this side, with 1/2 times sine of pi over 2x, we can leave that coefficient of 1/2 there for now. This, again, integrating a positive sign means that it's going to give us a negative cosine as an integration, because the derivative of negative cosine gives us that positive sign. Remember, we need to be in that mindset of continuously checking our work with integrals. So it's negative cosine of pi over 2 times x, leaving all that there. But then, because of the fact that we have pi over 2, we then need to go multiply this by, instead, a positive 2 over pi to cancel out with that coefficient. And of course, the ever so necessary plus c as a result of indefinite integration. Then with a little bit of cross canceling right there, we can then start our work. But first, we have a plus c to deal with. And they want to know the full function, especially with us giving the actual point f of 1 being equal to 2. Usually, even though this might be a little bit messy, this is the best time to then isolate for c, so that you can keep that value there as you move it across without having to deal with any other problems. So with that, let's have a look. If x is equal to 1 and y is equal to 2, we can then start plugging everything in here as a way to solve for c. So 2 goes in the place of y on the left side. Then with a negative cosine of pi over 2 multiplied by 1 for the x, all divided by a pi, and a plus c waiting to see what that will turn into. Cosine of pi over 2, thankfully, all goes to 0. And then 2 plus 7 is 9 to the 1/2 power, making it a 3 times 2. So this 9 again will go to 3. So times 2 makes it 6, being equal to 0 plus c. And so with that, c is equal to a positive 6. And so that takes care of that for this part right now. Okay, so our last lines of work here is going to be then to isolate y now. So it's y plus 7 all to the 1/2 power being equal to the negative cosine of pi over 2 times x, and then all over a pi coefficient plus 6. Okay, so with that, we just need to go run through this line of work here. We can divide 2 on the entire equation, and then we'll square it after the fact. So let's get y plus 7 being equal to, and leaving that 1/2 there for now, this is going to be negative cosine of pi over 2 times x all over 2 times pi, and then plus 3, because we can distribute that divided by 2, and then we square everything first and then subtract the 7 afterward, keeping track of that line of work there. So again, all of this needs to be squared first, so it's cosine of pi over 2 times x all over 2 pi plus 3, all of this squared to cancel out that 1/2 exponent, and then we subtract the 7 on the outside. Again, order very important because the 7 was inside the exponent, but with that, that y becomes f of x with everything else listed out there on the other side, with everything, and I mean absolutely everything, accounted for. Yes, indeed, this is going to be a nice problem that will most likely be asked in a similar fashion on the AP exam. So hopefully with that kind of walkthrough, that should be good for part number 4, and we can get to our last and final part to conclude our hour together. This is it. You've made it. This is the very last part for us to go over for the exam. I know, it's crazy, but we still have one more part to go over of volumes and slope fields. So first, imagine if we have the two-dimensional area of this, and we get something like this, where we have our two-dimensional rotated about an axis to get a three-dimensional solid. Oof! What a way to go about this one. Well, we have a few more rules and equations for you to memorize, and then we can go to some problems and examples exactly taken from all the AP exams. So, let's get first into the order of business, that understanding that of course we would need to integrate to get this area, then do a little bit of manipulation so that we can then calculate for a three-dimensional volume. Of course, if we understand that the area is simply going to be the definite integral going from a to b for any sort of function, f of x, in the sense that if we want to then expand it, the idea is that a function by itself is going to be one-dimensional, then taking the integral will bump us up to an area in 2 dimensions. Imagine if we were to take a volume and we were to rotate it, think of it as, right, we're rotating it circularly around pi one time, and then for the same function, just squaring it. That way, we can end up with a disk going about, right? Think of it as almost like there is a radius for a circle. Squaring it, multiplying by pi, you get yourself an area based off a circular motion. But then, by integrating all the way across all the different circles going from A to B, we can get our volume. First off, of course, this is when we're dealing with a disk, a singular full solid of a circle being rotated about an axis, and that is pretty simple for us. But then, sometimes they might ask you, well, forget the circular bit, what if then we extended it outwards as if it were a square coming off of the plane of the blackboard that we're on right now, and we could make 3 dimensions going across by pulling out squares in the 3rd dimension. Well, if in that case, the cross-section, idea is that if we were to cut it down, right, a cross-section is going to pull squares off of it. If we are dealing with that sort of a volume, in that case, that volume is going to be the same exact integral. It's just that it's going to be the base and squaring that in respect to x. What would be the base? Well, for the most part, that will simply just be the distance between the axis and the function. Sometimes not, and we can get into more examples on that in a little bit. Of course, if the distance just is strictly from the actual axis up to where the function ends, that's just going to be, in this case, just f of x squared. Pretty simple. But then if we continue, we can do other geometries too. Imagine instead of a square, we have a right triangle. Right? We have ourselves a triangle that's going to come up off of here. So let's think of it as one of the legs coming up there. We go vertically straight out and all the way down, and we have our right angle there. Not the best drawing, but you get the idea. Instead of doing one full square, we just do a right triangle with one of the legs being on the function itself. Well, if it was a right triangle with a leg on the function, then with that, we will be able to then understand that all we need to do is slap on a nice 1/2 coefficient, because a right triangle is 1/2 of a square, and we still go the same business of squaring the function again. Okay. Now, one last option that could be possible is that if they really want to screw over some students, they say instead of having the leg of the right triangle on the actual function, what if we flipped it in the sense that the actual hypotenuse is going to be the function itself, and as we move across from the limits of a to b. Now that one might get a lot of students. All it really takes is just a little bit of moving around geometrically, especially given the fact that the right triangles will almost always be isosceles, so the two legs peeking out of the function are exactly the same size. So with that, again, with the hypotenuse is going to be f of x. Just a little bit of geometric movement really just makes it so that you just need to do 1/4 of the same exact business, so that you can end up with the correct result dealing with an actual volume of that kind of a function. Okay, so that's pretty simple, but what if we swapped it to something where there is negative space, like this? A washer? What's a washer? Well, think about it like this. We have now, instead of just one function to deal with, we have f and g, but we only care about the area that's in between those two curves. And then we rotate it, which means when you take a look, obviously for what we shaded, we don't want any of that in there. We don't want any of that negative space to take up any of that volume calculation. Well, what do? Well, of course, there's a very simple idea here, where if we want to find the volume of something that is going to be rotated, where we take out, think about this, right? We have one circle out here that's going to be rotated about the axis, but also we have another circle there which needs to be removed from that volume as you rotate it about the axis. Well, would you look at that? The principle here will always be known as the top function minus the bottom function, right? That way we can remove the areas that we don't want, and then we integrate it across, making sure that when we turn it to a volume, all that we do not want is going to be cut away from our calculation. Very nice. So as before, because we are rotating about in a circular motion, we're going to need that pi coefficient waiting for us outside on the actual equation here. Then of course our limits will be going from a to b, from where we're going to start and finish our calculations. Then from there, again, the idea still holds. If f of x is the top function, the one that carries the most area, while g of x is the bottom function, which includes the distances that we want to remove from the actual calculation. In that case, I like to describe it as big R squared minus little r squared dx. What does that mean? Again, when we think about it in the sense of circles that are spinning around this entire axis, the bigger r is the larger radius, which then we take out the little radius. Remember that we're squaring them individually because you think of it as taking one area away from the other, and then we integrate it across our limits. So in this case, if we draw the connection from what we have on our drawing here, this will be pi multiplied by, from a to b. In this case, the function f of x is the larger of the radii, and then the g of x is the one that we want to take away from our calculation. So with that, that is going to be the way that we can calculate for that volume. Okay, so all it really takes is just a little bit of extra analysis on our end to really understand where the radius is going to be when you draw out these circles as they become rotated about the axis. Now, when we look at an exact problem like this, which is very legal but very wacky problem that the AP exam could ask for, taken exactly from the 2019 AP exam. We have right here the region of R locked in between the graphs of h of x and g of x, but the actual problem itself states that we are going to write out, we don't have to solve for, but we need to set up that actual integral expression where if we took that region of R and rotated about y is equal to 6, the horizontal line, what do we need to show for our work here? So imagine we have the y is equal to 6 line right there, and then we use that to rotate as this entire section is then rotated about that axis up there, spinning it around, and as you can see, we do have some negative space we still need to remove from our calculation to make this match. Well, let's have a look. Remember, as always, it's the top minus bottom prospect for us that needs to be remembered, as well as the fact that we are measuring in terms of different radius. So it's big R squared minus little r squared, and we need to sort out which ones are going to be which. Well, let's have a look here. If we have the larger radius, as you can see from what we drew out in terms of how much the distance is going to be from our calculation, the larger radius is going to be the distance between the y is equal to 6 line and that g of x, which is that bottom function that goes down into the negative area on the graph. Well, pretty simply put, we can already set up our larger radius is going to be 6 minus the g of x function, because it's the whole distance. Then we take off the g of x. Now you might be thinking, well, if we take off g of x, wouldn't that just make this really small? Well, again, as we might have noticed, is that we have all of this negative area underneath the axis, resulting in negative y values. So if you subtract g of x, that would actually add to the radius to include the entire distance from 6 all the way down to the bottom of g of x there. In that case, our smaller radius then obviously needs to be just this small area that we need to then remove, which we can describe as 6 minus h of x, that top function, which then needs to be removed, as we left alone with all of our negative space that we can rotate about. So actually, going through here, it actually turns out that our limits are going to be from 0 all the way to positive 2. That's where the graph ends for this. So with that, all we need to do is set up our definite integral here. That with our volume is going to be, always remember, you need that pi coefficient because we are rotating in a circular fashion. That is extremely important to make sure we have in there. Our limits will go from 0 to 2. And then remember, the formula function is going to be r squared minus a big R squared, that is, minus little r squared. So with that, we just do 6 minus g of x, the larger radius of the two, and then we square all of that, subtract it by the other side of 6 minus h of x, which is the smaller radius, and we square all of that and integrate in terms of x because we're just going vertically across the x limits over there. And there you have it. This is exactly what they want to see on this exam work right there. You cut off those 2's a little bit there, but that's still to the second power as shown with our work. And that is exactly what they want to see for us to be able to fully understand how to set up an integral for a volume. Other times it will make you actually solve for it, but in this case, not really, because this is a bit too complicated for a non-calculator section, which this was taken from. So let's get to our very last point of slope field. Oh, that looks very different now, doesn't it? Yes, indeed, there are times in which they will give you a differential equation and they'll draw these little tick marks across this coordinate plane for us to see what these slopes look like as you move across both the x and the y. Again, the idea is that this is called a slope field, where you could notice where those derivatives will result in based on the x and the y's. So a classic question that is asked is that they want us to, with their given of the differential equation for the slopes coming across both the values, that we want a solution curve through a specific point, 1, 0.5, which they very easily pointed out for us on the graph. Might seem daunting at first because we got all these little tick marks going all over the place, but if you keep your head cool, you can keep up with the fact that all you need to do is just follow the ideas of where those slopes are taking you, and then you just roam your way across these different points. For example, if we're going to start at the 1, 0.5, you realize that we end up with slopes that are going to flatten out because we have our derivative of 1 over x with larger x values resulting in much shallower slopes as we get closer and closer to 0 with an increase in x. So all this really means that you just got to follow this along and go there. Again, we're not trying to connect any dots here, but keep in mind of making sure we flatten out over there and then we continue downwards through because although we can't get to 0 because 0 makes it an undefined slope, we get very close to it going the other way. And with that, that actually would be very acceptable on the AP exam by the test graders. Most of it isn't going to be very exact points unless they ask for them. Most of it will just be making sure you're following those guidelines of where the slopes are going to go with a possible solution. All right, and would you look at that? Our hour is up, and it looks like that will do it for our main ultimate calculus study video. So hopefully this can be used while many of our students go back to College Board and look at some actual free response questions, and they should be able to answer them after all that we went through today. Very good. That will do it for me. And the next time that you might see me on this channel, we'll be actually going over a lot more fun subjects like chemistry. So good luck on that exam, and I'll see you there next time.